All right, welcome to lecture 3. In this lecture, we're going to talk about inference and single factor designs. So really, this is the classic lecture on analysis of variance, but I'm kind of getting ahead of the game at this point. So what I would really like to do is start with an example and then kind of show you what it is that we're going to be talking about and what you can get out of this lecture. So here's kind of a guiding example for us. Let's suppose you have an IO psychologist who has studied 3 computer keyboard designs, and then subjects were randomly assigned to type on one of the 3 designs, either keyboard 1, 2, or 3, and the number of errors was recorded. So here you can see that we have a design where there's 5 people who were randomly assigned to keyboard 1, and here are the numbers of errors that each of them made, and the mean was 1. Keyboard 2, you see the data there, as well as keyboard 3. You can see that there appear to be some differences between the keyboards, and you might want to make some inference about the overall efficacy of these keyboards based on these observed data. So we're going to talk about how to answer questions like that using a classic technique, particularly the analysis of variance. But to get there, we really need to delve into some of the conceptual underpinnings of what really builds up analysis of variance. Because if you've had a statistics course before and you've seen ANOVA, which is the shorthand word for analysis of variance, it may have been presented as a collection of formulas that you have to apply. And while there are certainly some formulas that you have to apply, I want to argue in this lecture that they are formulas that are natural and they are just extensions of things you've been doing already, and the procedures overall are just simple examples of the overall framework of hypothesis testing that you're already familiar with. So let's see how we do with that. So to answer questions about these data, which is our goal, what we first need to do is put some structure on the data. So I want to argue that these data, as you see them, are really just kind of random stuff. And we really can't see anything about these data until we put some sort of structure. And what do we mean by structure? Well, we mean 2 things. First, let's look at some visual structure. One thing you might do is just plot the raw data. So here on the horizontal axis, I've put the keyboard number as 1, 2, or 3, and then on the vertical axis, I've put the number of errors. And I've indicated each of the data points with a little crosshash. And there are 5 in each column, although there are some repeats occasionally, which is why it appears that there's only 4 here. There's actually 2 different people who scored 6 errors. So there's 2 data points right there. And something similar happens with keyboard 1. Now, that seems to get a little bit more structure, but I will claim that the most often used structure that we place on these data is we simply look at how do the means compare. So let me draw what I mean by this. I'm going to get a red pen. And so you might recall, let's look up and remember real quick, the mean, it's actually there. I don't have to scroll up, never mind. So look up here, we can see the mean of keyboard 1, the mean number of errors was 1. So I'm going to put a little circle right there at 1 to indicate that that's the center of those data. For keyboard 2, the mean was 5, so I'm going to put a little circle right here to indicate that mean. And then for keyboard 3, the mean was 6, so I'm going to put a little circle right there. And then I'm going to just visually connect these. There's no really any particular reason for doing that, just to see that now when we look at this, we can see, okay, there's some order to these data, there's some structure, there's some rhyme or reason about how these data are observed. And really what I mean by this, I'm sort of waffling all over the place, which is the problem with verbal definitions, is that this structure shows us real quickly keyboard 1 seems to be really good compared to keyboards 2 and 3. What exactly do we mean by that? We have to be more specific, but I think you can begin to see some structure here. So let's formalize this. Let's get rid of all this hand waving and let's actually impose some structure on these data by way of a statistical model. Okay, so that's where we want to go first. So what do I mean by a statistical model? Well, what I really mean is we're going to write down a formula that generates each of the observed data points. So we have 15 data points to deal with. I want a formula that's going to produce each of those observed data points, those observed errors in this case. In words, what I'm really doing is I'm generating a data story. This is the story of the data. Now, there are a lot of ways to do this. The one that I'm going to show you first is what's called the linear model. And the linear model is by far the most often used in our discipline. And it might look something like this. This may, if it's not familiar to you, then that's just fine. This will be all you need to know for now. The formula looks like this. It's x with two subscripts, and I'll say what those subscripts mean in just a second, equals mu sub j plus epsilon sub ij. Oh my goodness, what is all this? Well, let's define what these symbols and these subscripts mean. So the first thing that I want to define are the xij's. So the reason there are two subscripts is because the x's need to be specified at two levels. They need to be specified for the subject number, that's denoted by an I, and that I is going to be subject 1, 2, 3, 4, or 5. And then they also need to be specified for a condition number, 1, 2, or 3. So that's the keyboard number in this case. And so essentially that gives us 3 times 5 or 15 different values that we can denote by a specific combination of I and j. For example, if we wrote down, let me change it back to this bluish color, if we wrote down x sub 1, 3, okay, that would mean the first subject, I equals 1, in the third condition, keyboard 3. Okay, and then we would also do x2, 3, x3, 3, etc. And we're not really ever going to write these down, but in the abstract, that's what this notation represents. What about the mu's and the epsilons? Well, the mu j, that is the population mean, as you would expect, for condition j. So j is indexing conditions here. And again, j would be 1, 2, or 3. So that means in this equation, I'm encoding 3 possible mu's. Mu1, which is the population mean for keyboard 1, mu2, or mu3. And then what's this epsilon? This is probably new to many of us. This epsilon is an error score, essentially, and I don't mean error on keyboard typing, I mean error from the mean. What exactly I mean by that is it's the deviation of subject I in condition j from the condition mean mu j. Okay, so in other words, it's the error that the model produces. Let me explain what I mean by this by going back to the picture. You may have wondered why I drew this picture. Well, here's why. When we put that red picture inside our raw data, we're really putting a simplifying model. All right, this is a simplifying model so that we don't have to pay attention to every data point here and every data point here and every data point here. We're saying keyboard 1 tends to be lower than keyboard 2 and keyboard 3. We can see that by only focusing on the red. But if we really want to generate each of the data points, we have to say, okay, this person right here, they're not exactly equal to the condition mean, which is here. To get there, we would have to add some extra deviation or some extra measurement error to get this person's actual data point. Same thing with this person down here who scored 0 errors. They scored less errors than the condition mean, so we would have to subtract 1 from the condition mean to get their actual score. Same thing over here. Each of these 5 data points can be thought of as the condition mean plus some specific subject level variation. And then finally, same thing over here, condition mean plus this much, or this much, or this much. So really all this is a formal mathematical way to say that we can write each observed score, each of the raw scores, as the sum of 2 things. 1, the condition mean, and 2, some individual variation around that condition mean. Okay, so those 2 things are right here. So why are we doing this? Well, we're doing this for 2 reasons. One is we're doing this so that we can say exactly what we mean when we get to hypothesis testing. So we need some symbols to represent things that are actually kind of hard to say and hard to write down. And 2, we want some model to place on the data because in the end, we can't handle the raw data. It's messy. We need to impose some structure, some simplifying assumptions, and that's, believe it or not, what this model starts to do. Now, we're going to see that a lot more this semester, but this is kind of the indication there. So from this, our inference goals are simple. Just like any inference, we want to test hypotheses about something. Specifically, we want to test hypotheses about the condition means, the mu j's, and we also want to estimate those condition means. And we're going to learn how to do that now. So let's start with hypothesis testing. Now, first, let's consider two hypotheses. These might be natural to consider. In fact, they are the ones we will consider in these kinds of designs. We consider a null hypothesis. Now, remember, a null hypothesis means no differences in things. So that would mean that these condition means are all the same. No differences between them. mu1 equals mu2 equals mu3. The alternative, H1, is going to be not that. Well, the null hypothesis is that they're all equal. Thus, the alternative hypothesis will be that they're not all equal. And so I just write it this way, not all mui's are equal. Now I ask, which one of those better predicts the observed data? Now remember, if we take a frequentist approach, which I'm going to do first, what we want to do to answer that question is compute the likelihood of our observed data if the null is true. So how does that work? Well, the way it works is we go back to a technique that was developed by R.A. Fisher. And this goes all the way back to the 1920s. And he developed what I think is a really creative method for computing this likelihood. And that method boils down to partitioning the variance in the observed data. Let's draw a picture to indicate what we mean by this. What Fisher figured out, and I'll show you exactly what he figured out in a moment, is that if you take the total variance in, say, those 15 data points, the total variance from the mean overall, then you can actually write that as a sum of two things. You can write it as the variance between the treatment groups and the variance within each of the treatment groups. So it's kind of like you're taking the total variance and splitting it into two components, and their sum will be that total variance. Now, why is this good? Well, this is good because Fisher figured out that if you then compute the ratio of those two variances, specifically if you compute the ratio of the between treatment variance and the within treatment variance, like this, we call that F now for Fisher, that ratio, that statistic, if you will, has a really interesting property. Namely, that under the null hypothesis, that statistic forms what's called an F distribution, and it looks like this thing right here. So it gives us a sampling distribution that we can then compute the likelihood of observed data on under the null hypothesis, just like a normal distribution or a t distribution. This new distribution is now the F distribution, and it is what we are going to use. Okay. Now, before we get into how to figure out what that F score is, I want to show you already have the tools available to calculate probabilities, particularly p-values, with the F distribution, and it's in the distribution calculator that we have used this semester. Let me reload this real quickly. So you might remember we've used the normal and the t distribution, but we haven't so far used the F distribution. Now if we click on that, we get that, and you get this skewed distribution. So we'll come back to that and actually compute something with it very soon. But just know we have a tool for computing p-values in these designs. So how does this work? How do we compute these two different variances? Once we've got that, the game is over. Well, what we need to recall is what variance is. Variance is the sum of squares divided by the degrees of freedom. That's just what it is. Go back to your first stats course, that's all it ever was. So that means we need to compute two different types of sums of squares, SS's. We need to compute a sum of squares between group means and a sum of squares within the groups. And then we'll take those and compute the variances from them. So let's start with the SS between. To compute the SS between the group means, what we really need to do is something simple. We simply want the sum of the squared deviations between each group mean and the overall or grand mean. All right, so we want to take this group mean and see how different it is from the overall mean, and then square that. And then we take this group mean and see how different it is from the overall mean, square that, etc. We just do that for however many groups we have. What does that look like? Well, it looks like this. You take this top row, which is exactly what we just said. We take the first group mean minus the grand mean and square it. And then we do that for the second group mean and the third group mean. If we sum all those together, we can write that in a nice compact notation like this. The sum as j goes from 1 to 3 of xj bar minus x bar squared. So that's the sum of squares between the groups, almost. Okay. Why do I say almost? In other words, why have I not put a box and shaded this yellow to show you this is how you do it? Well, here's why. There's a little technical note that we need to address. So this sum of squares, when we divide that by the appropriate degrees of freedom, that's going to give us a variance. Particularly, it's the variance of the distribution of sample means. I'm going to denote that as sigma squared sub means, okay? Because these are how means are distributed around the grand mean. By the central limit theorem, that variance is what you get by taking the variance of the subjects and dividing by n. Now, use a little bit of algebra and we can solve for the variance of the subjects. Just multiply by n on both sides. Now, why does this matter? Well, what this matters for is because it says that we're going to need to multiply by n, this part right here, in order to scale up that sum of squares to get onto the level of variation among subjects, which is what we're really after. We're not just interested in variation among means. We want to make sure that that's at the level of subjects as well. So what that means is we take that little sum that we wrote up there, and then we multiply it by n. And that gets us something that's on the right level of measurement. And that's what we define as the sum of squares between. We take n, which is the number of data points in each condition, and then we multiply it by that sum that we just described above. Okay. We talked a lot in the abstract. Let's actually do it for our data now. So for our data, just to recall what those means were, they were 1, 5, and 6 respectively. The overall mean, it's easy to figure out that overall mean is 4, and n is 5. There are 5 data points in each group. So how does this work? Well, the first step, we write down the formula, so it's n times that sum. Let's expand what that means. We put in 5 times. Now the sum is we take the first group mean minus the grand mean, 4, and square it. Then we take the second group mean minus the grand mean, square it. Take the third group mean minus the grand mean, square it. Okay. Let's figure out what all those are. This is 3 squared, 1 squared, and 2 squared. So that simplifies as 5 times 9 plus 1 plus 4. Take 9 plus 1 plus 4, that's going to be 14. 5 times 14 is, oops, I got rid of one thing that I shouldn't have there. That is 70. So the SS between is 70. What do we do with this? Well, we want to convert it to variance. So we're going to do that. Just a quick note, in this technique, we often write variance as MS. We don't do that much of anywhere else, but MS literally means mean squared deviation, which is all variance is. So that mean squared deviation, or the variance between groups, is just the sum of squares between groups divided by the degrees of freedom between groups, just like any variance. Well, the sum of squares between, we just figured out, right? That was the 70. DF between is going to be 2. Why is it 2? Well, 2, remember, any degrees of freedom is going to be the number of something that you're dealing with minus 1. This is just simply the number of groups minus 1. We have 3 groups that we're comparing, so the degrees of freedom between groups is going to be that number minus 1, or 2. And if we do that, I shouldn't have put that there. Let me erase that little part real quick. There we go. If we actually do that computation, the MS between turns out to be 35. So the between groups variance is 35. Okay? So that's all there is to computing between groups variance. It comes directly from this formula right here. Oops. And then we simply divide by the appropriate degrees of freedom, which is the number of groups minus 1. Now let's talk about how to compute the sum of squares within groups. So for this one, it's a little more straightforward. What we do is we simply pool together the sum of squares within for each group. So let's write a formula to say what that is. It looks kind of complicated, but let's work from the outside in, or sorry, the inside out. This part right here, okay, this is the sum of the deviations from the group means. So the notation, if you really dig down to what it is, this says take this data point and subtract the appropriate condition mean. So if you're in group 1, you're going to subtract 1 each time. If you're in group 2, you're going to subtract that mean, which I think was 4. If you're in group 3, you're going to subtract 5. And then once you do that, you just simply add up all the group 1 stuff, add up all the group 2 stuff, add up all the group 3 stuff. That's what this outer sum is. So let me show you what that means. So the first level, we're going to add up all the group 1 deviations. So we take each of the data points in group 1. Those were 0, 4, 0, 1, and 0 respectively. And we're going to subtract 1 from each of those, the group mean. Okay? And then we do the same thing for group 2. Those data points were 6, 8, 5, 4, and 2. But this time we're going to subtract 5 from each one. And then finally we take the group 3 means and we're going to subtract, or the group 3 data, and we subtract that mean, which was 6 each time. So I misspoke a little bit earlier there, 1, 5, and 6. That's a lot of deviations. Let's figure out what all those are. They're all very easy to do in our head if we just take a look real quick. This is 1, 9, right? Take the difference and square it. 1, 0, and 1. So that's these guys. And do the same thing for the next row. And the same thing for the third row. Add all these numbers together, and we get a total sum of squares of 46. So we're just adding up all the deviations from the respective group means. Okay. Now we need to convert that to a variance. Okay. Of course, that means we divide by the degrees of freedom. What are the degrees of freedom? Well, since there are 4 degrees of freedom in each of those 3 groups, then we have 4 times 3 equals 12 degrees of freedom total within groups. Remember, we're pooling this all together. So we take the degrees of freedom from each group, which was 4, 4, and 4. Okay? So that gives us 12 degrees of freedom. So if we compute that variance, that MS, or mean square within, it's going to be that sum of squares 46 divided by that degrees of freedom 12, which turns out to be about 3.833. So finally, we can compute the F ratio. Okay. Remember, the F ratio, or the F statistic, is the variance between groups divided by the variance within groups. Notation-wise, that's MS between divided by MS within. We just figured out both of those. It was 35 divided by 3.833. If we do all that, it turns out to be 9.14. That's the F statistic. So we ask ourselves, how surprising is this observed data if the null is true? Well, that means we want to find the likelihood of getting an F score beyond 9.14 if the null is true. To do that, we simply go to our app. Okay, we choose the F distribution. Now here we have to specify 2 different degrees of freedom. We've got the numerator degrees of freedom. That's the between groups degrees of freedom. That was 2, remember? It was the degrees of freedom we used to compute that between groups variance. And then in the denominator, the within groups variance, we used 12 as the degrees of freedom. Now what that does is change the shape of the F distribution, just like the degrees of freedom does for the T distribution. And then we want to find an upper tail based on 9.14. And if we do that, we get that p-value. It's very, very far out there. It's a very small p-value. I'm going to write it down, then I'll switch to the screen. It's 0.00387. Okay. So we write that down. That lets us make some inference. Basically, we can say the data are rare under the null because that's a very small likelihood. And then thus we reject the null in favor of the alternative. Now that's the frequentist approach. So basically the work here we've already done. We just need to figure out how to compute this F ratio. And that's what we just learned. So of course I know your next question is, what about a Bayes factor? Can you do a Bayesian version? The short answer is yes, and I'm going to show you a quick and dirty way to do it. The long answer, we'll talk a little bit later in the semester about doing full Bayesian analysis of these models. It's a little beyond this lecture, but wait just a couple of weeks and we'll get there. So a quick and dirty approximation actually comes from some of the work that I've done. I'll show you the paper real quick, and I'll put a link to this in the video. This paper here, yes. So this is a paper in 2018 published in the journal Biometrical Letters. And I talk about how to compute Bayes factors from summary statistics, basically. If you give me an F score, I can give you a Bayes factor. If you scroll down through the paper, it takes a little while to get to it because I actually work out the details of how to get this formula. But the formula is this guy right here. It's equation number 6 in the paper. Whatever all that is, I'm going to write it down on my notes here in just a second, but you'll at least know where that comes from. Oops. So what we do is we convert the observed F to a BF01, and it's with that formula. And I think you can figure out what all those things are. The N is this little n is the total number of subjects in the experiment. DF1 and DF2 are the numerator and denominator degrees of freedom. Of course, F is the F statistic. If you put all that in, you get an answer. An easier way even to do this is to use an online app that I developed, and I described that app in this paper in AMPPS. So I'll put a link to that one as well. If you look through that paper, you'll see there's a little web app here. And I'll also put the address for the app, which if I reload it is right here. And it's just like any of the other apps that we've used this semester. You just look and see what it asks for. We put in our F statistic, which if I remember correctly was 9.14. And the DF1, that's the numerator degrees of freedom, that was 2. And the denominator degrees of freedom was 12. And it's a between subjects design. You can see here we get a Bayes factor of 68.98 for the alternative. So the observed data are almost 70 times more likely under the alternative than the null. Okay? So you can do this full sort of, or at least a partial Bayesian analysis using this calculator. It's probably worth something here. It's probably worth something to say about why do I keep calling this not a full Bayesian analysis? And the answer is because this number you get is an approximation to the Bayes factor. It does something called the BIC approximation, which we might talk a little bit about later this semester. To get a full sort of exact Bayes factor, we've got to do some different things, and that's coming soon. So it's about time to end this lecture. We've gone on long enough, but I wouldn't want to stop without talking about how to do estimation. So let's talk about how to get a confidence interval. Let's pick one of the means. Let's pick mu2, the condition mean for keyboard, or sorry, the population mean for keyboard 2. How would we do that? Well, you know how to do a confidence interval at this point. You take the mean and then you add plus or minus a margin of error, which is this t star df, this critical value of t times sigma hat divided by the square root of the sample size. Now the subscripts all just indicate that we're in the second group. So how do you find all these things? Well, we need 3 things. We need the condition mean, which is pretty easy to get. Right, that's just 5. We already knew that from the data. T star df. What we do there is we go back to our distribution calculator and we figure out the critical value that leaves 5% in the tail of the t distribution. The big question is, what degrees of freedom do we use? And you use a degrees of freedom that is based off of the size of the size of the group that you're estimating the mean for. So this second group had 5 data points in it, so our degrees of freedom will be 4. And if we use that degrees of freedom, we get a critical value of 2.78. And then finally, this is the big news today, what is the standard deviation? Well, the standard deviation is going to be the square root of the variance. And the variance you've already estimated. It's that within groups variance. What the ANOVA does, the analysis of variance, basically pools all of those variances into a single group estimate. That's why we divided by the total degrees of freedom within groups. And so all we need to do is take the square root of that variance. We take the square root of MS within, which was 3.833, and we get, oddly enough, 1.96. That's a complete accident, but that's what we get for our estimate for the standard deviation. So put all this stuff together. Our 95% confidence interval will be that sample mean plus or minus t star df times the standard deviation divided by the square root of the group's size. And that's 5 plus or minus 2.44, which gives us this confidence interval. So we're 95% confident that that mu2, the population mean errors for keyboard 2, is somewhere between 2.5 and 7.5. So that's all for today. I didn't go into a lot of detail on computing ANOVAs. We'll do more practice of that in our class session, but this should give you some of the conceptual underpinnings of what ANOVA is all about. Basically, it's all about splitting your total observed variance into 2 sources and then figuring out how to compute those 2 different variances. Take the ratio of them, and that's your F-score, and you use that F-score to do your inference. So that's all it is to it. So, hope you enjoyed that, and we'll see you next time.